In part A, we have a product of two functions. That is, we have x times sine of x. I need to use the product rule to take the derivative. F prime of x is equal to the derivative of the first times the second plus the first times the derivative of the second, and the derivative of sine of x is cosine of x. This is the derivative. I think I'll just write this as f prime of x is equal to, I'll simply put it's sine of x plus x times cosine x. The function in B is again a product of two functions. So here, f prime of x is equal to the derivative of the first times the second plus the first times the derivative of the second. And the derivative of cosine of x is negative sine x. That's a fine answer, but I think I'll just simplify it a little bit. Let's see, this is 3x squared times cosine of x minus x cubed times sine of x. This could also be factored. Let's see. You can remove an x squared from both terms and leaving this as 3 cosine x minus x sine of x. I really don't think any are like preferable, but you could leave your answer like this one here. In part C, we again have a product of two different functions. So when I take the derivative, it's the derivative of the first, which is cosine of x, times the second, which is also cosine of x, then plus the first times the derivative of the second, which is negative sine x. This can be simplified a little bit. This is cosine squared of x minus sine squared of x. And I think I'll leave the answer just like this. For part D, I think I'm going to rewrite this function a little bit. So I'm not yet taking the derivative. I'm just going to express this as 1/3 times tangent of x plus 18 plus, and I'll put x to the negative 1 times sine of x. That way I can use the product rule on the last term. So to start with, the derivative is going to be 1/3 times the derivative of tangent, and the derivative of tangent is secant squared of x. The derivative of 18 is 0. Now, on to the derivative of x to the negative 1 times sine of x. This is negative x to the negative 2 times sine of x plus x to the negative 1 times cosine of x. You could leave the answer like this, but I guess I'll simplify it a little bit. This is 1/3 times secant squared of x. I don't need the 0. I'll put minus x to the negative 2 times sine of x plus x to the negative 1 times cosine of x. You could rewrite this so the exponents are positive integers by putting them in the denominator, but I think this is good enough for this problem. For part E, I don't see a good way to rewrite this as a product of two functions, so I'm going to have to use the quotient rule when I take the derivative. So that is, the derivative is equal to the derivative of the numerator. Okay, that's going to be, well, the derivative of 1 is 0. The derivative of cosine of x is negative sine. This extra negative changes it to positive sine. So this is the derivative of the numerator. I'll write it as 0 minus the derivative of cosine is negative sine of x. The denominator, which I just copied down, is 1 plus sine of x. And then we reverse this process. Copy down the numerator. And the derivative of the denominator is cosine x. This is all divided by 1 plus sine of x. And you could stop here, but I think I'll simplify it a little bit. Let's see. So this is sine of x times 1 plus sine of x. Then we have minus. If I distribute in the cosine, I get cosine of x minus cosine squared of x. all divided by 1 plus sine of x all squared. And I'm seeing I forgot the squared in the denominator in the first line. Okay, to continue, all right, I think I'm going to multiply in the sine of x. So we get sine of x plus sine squared of x minus cosine of x plus cosine squared of x, all divided by 1 plus sine of x squared. Okay, this is, let's see, there's an identity that I'm going to use. Sine squared of x plus cosine squared of x is equal to 1. This means I can replace sine squared plus cosine squared with 1. The numerator is really equal to 1, which comes from sine squared plus cosine squared, plus sine of x minus cosine of x, all divided by 1 plus sine of x squared. I don't really want to go any further with that one. This is good enough. Okay, for part F, partition this off a little bit here. All right, if I want to take the derivative of this, oh, here we have a product of two functions. So it's one function times another. All right, let's see. I have to use the product rule. So the derivative is going to be the derivative of 2 to the x, which is 2 to the x times the natural log of 2, times secant of x, plus, okay, now I leave 2 to the x alone, and I multiply by the derivative of secant. And the derivative of secant is secant x times tangent of x. That is the derivative. I'm going to try to fit it in one line. So that's f prime of x is equal to, all right, we got 2 to the x times the natural log of 2 times secant of x plus 2 to the x times secant x times tangent of x. And if you want to factor, you can. It looks like from both terms we can take out a 2 to the x and a secant of x. And what is left over is the natural log of 2 plus tangent of x. I don't really think one is better than the other, but I'll put this as my answer here. For part G, I see that we have a product of two functions, a first times a second, but I'm going to rewrite this. So the part I'm focusing on is the square root. I'm going to put it as x to the 1/2 power. And then I'll identify this is my first and this is my second. So when I find f prime of x, I take the derivative of the first, which is e to the x, and then I multiply it by the second. I then leave the first thing alone and multiply by the derivative of the second, which is 0, plus 1/2 x to the negative 1/2, plus the derivative of 5 to the x is 5 to the x times the natural log of 5. I really think that's good enough. However, I think what I'll do is I'm going to factor out an e to the x, leaving me with these three terms and really these two terms over here. And I see you can combine a 5 to the x and a 5 to the x times the natural log of 5. So I think I'll kind of do that in one step. This is not necessary. It's just one way that you could rewrite the answer. So that is, you factor e to the x out from both terms. I'll then copy down 1 plus x to the 1/2 plus 5 to the x. And then I'll copy down these terms, but I'll leave off the 0. So you get plus 1/2 x to the negative 1/2, and then plus 5 to the x times the natural log of 5. And yeah, you could combine the 5 to the x and the 5 to the x times the natural log of 5. You could put this exponent into the denominator by making it a positive 1/2. But I mean, this is good enough. I'll say that this is the answer. Part H is pretty complicated, but I see I can divide x cubed to the three terms in the numerator. So I think this is a good problem where you can rewrite it. This is x squared times sine of x over x cubed plus 1 over x cubed plus x cosine x over x cubed. That way, this x squared cancels to leave me just x to the first in the denominator. This x cancels with that 3 with 2 left over. And then I can move these x's to the numerator by making their brand new exponents negative. So f of x is actually equal to x to the negative 1 times sine of x plus x to the negative 3 plus x to the negative 2 times cosine of x. What I'll do is take the derivative on the first piece. I'm going to use the product rule, and I'll do the same thing on the last piece. Let's see what we get. So no derivative just yet, just like rewriting the function. F prime of x is equal to, okay, the derivative of the first is negative x to the negative 2 times the second, which is sine of x, plus, leave the first alone and multiply by the derivative of the second. I then take the derivative of the next piece, which is negative 3x to the negative 2. And now I have to use the product rule again. I take the derivative of the first. I then copy down the second. And then I add on, leave the second alone, but multiply by the derivative of the first, which is negative sine of x. I mean, here it is. It's not simplified, but we did, in fact, take the derivative. Does anything like really combine here? Maybe I'll rewrite this so all the exponents are positive, so it looks kind of like our original expression, just to see what that looks like. F prime of x is equal to, okay, this first piece is really negative sine of x over x squared. Then plus, okay, we get cosine of x over x to the positive first, minus 3 over x squared. Then we have minus cosine x over x cubed. And then minus, this minus comes from, well, this is really negative. It can be multiplied out front. And we get sine of x over x to the positive 2. Wow, this thing. I think what I'll do is on the next slide, put this all into one fraction with a common denominator. So that common denominator will be x to the power of 3 because that is the largest one. So let me copy this down. So here was the previous function that we had. I know I want a common denominator of x cubed, so I can multiply the first fraction by x over x. The second fraction I can multiply by x squared over x squared. The third fraction I can multiply by x over x. I don't have to do anything to cosine x over x cubed, but here I can multiply by x over x. What all this does is gives me a large fraction here, large fraction, whose denominator is x cubed. Okay, the first piece is going to be, I'll write it as negative x sine x. Okay, then plus x squared cosine x minus 3x minus cosine x minus x sine x. Are there any common terms or anything that cancels? Not a whole lot. I do see that, well, I can combine this with this. So, all right, I'll write my answer as f prime of x is equal to, okay, that's negative 2x sine of x plus x squared cosine x minus 3x minus cosine x all over x cubed. So this would be a simplified answer, I suppose, but there it is. For part I, I'm going to rewrite the function, so not yet take the derivative, but I'm going to write it as x to the 1/2 times secant of x. And note that this is a product of two functions. So f prime of x would be equal to the derivative of the first, which is 1/2 times x to the negative 1/2, times secant of x, plus the first, which is x to the 1/2, times the derivative of the second, which is secant x times tangent of x. This thing. I think that's good enough. We can leave the answer just like this. You could factor some things out. You can make some exponents positive, but I think that's good enough. For part J, again, I see a product of two functions. All right, let's see what we get when we take the derivative. F prime of x is equal to the derivative of cosecant, which is negative cosecant x cotangent. Then we multiply by secant. Okay, we then add on. We'll leave cosecant of x alone and multiply by the derivative of secant, which is secant x times tangent of x. I mean, I guess that's it. It's good enough. But I guess this could be simplified. I mean, maybe some things cancel or combine. Let's see. Well, to start with, I see we could factor out a cosecant secant from both terms. So let's try that. If we do that, if we take out cosecant x and secant, what is left over is negative cotangent and positive or plus tangent. Okay, can we simplify this thing? Again, this is really just for practice here. We already took the derivative, but one direction to go is you could always convert everything in terms of sine and cosine. In doing this, maybe you could see what cancels a little bit easier. So I'm going to replace everything in terms of sine and cosine. All right, well, the definition of cosecant is 1 over sine of x, and the definition of secant is 1 over cosine of x. Okay, negative. The definition of cotangent is cosine x over sine x, and tangent is sine x over cosine x. Wow, where to go from here? I guess I'll get a common denominator and add these two fractions. So the common denominator would be sine times cosine. So I guess I'll multiply a cosine in here and a sine in here. So we get f prime of x is equal to, I'll write this first fraction as just 1. It's just 1 divided by sine x times cosine x. Here we're going to have a common denominator of sine x cosine x, and the numerator is going to be, it's going to be negative cosine squared because we were multiplying in a cosine. And then over here we're multiplying in a sine, so I'll put plus sine x. And we get this. We could now multiply this into here. That's a sine squared plus cosine squared. I'll do that on the next slide. All right, so when I multiply this denominator here, we're going to increase the exponent by 1 on both sine and cosine. So f prime of x is equal to, let's see, that's negative cosine squared x plus sine squared x, all divided by sine squared x cosine squared x. Let's see. I mean, I guess that's fine. We could leave it like this. We could also split this up into two separate fractions, canceling a cosine squared and a sine squared. So I guess, I mean, f prime of x is equal to, well, this is negative cosine squared x over sine squared x cosine squared x plus, okay, sine squared x over sine squared x cosine squared x. So that this cosine cancels with that cosine, and we really have negative 1 in the numerator. This sine squared cancels with that, and we have a positive 1 in this numerator. So we could express the answer as f prime of x is equal to -1 over sine squared of x plus 1 over cosine squared of x. And we could then convert these back to the definitions of secant and cosecant. 1 over sine is cosecant, so this first fraction is really negative cosecant squared of x. And the second fraction is going to be secant squared of x. Not really sure if any of these are better than any of the others, but I'll leave this as the final answer. Before proving the identities in question 2, I want to again write down the fact that sine squared of x plus cosine squared of x is equal to 1. This is a fundamental identity. In fact, it's called a Pythagorean identity for trig functions. All right, so I want to prove that the derivative of tangent is equal to secant squared. How would you go about doing this? The way to do it is to rewrite tangent as a fraction, sine over cosine. Because you know how to take both the derivative of sine and cosine, and we have the quotient rule. The quotient rule says you take the derivative of the numerator, derivative of sine is cosine, and you multiply it by the denominator, which is also cosine. You then subtract off. Okay, now we leave the numerator alone, but multiply by the derivative of the denominator, and the derivative of cosine is negative sine. And this is all divided by the denominator, cosine, except it's squared. All right, we have to simplify this now if we're trying to prove this formula. So what can we do? Well, cosine times cosine, I would write as cosine squared. This minus and minus becomes a positive, and we have sine times sine, which is sine squared. And this is all divided by, instead of writing cosine x squared, we'll write this as cosine squared of x. They're the same thing. Well, this identity actually shows up in the numerator, except it's backwards. Sine squared plus cosine squared is equal to 1. And technically, this is it, but only because the definition of 1 over cosine is secant. So this proves our formula. All right, how do we prove that the derivative of secant is equal to secant tangent? Why is this true? We're going to rewrite this as the derivative of 1 over cosine. That is the definition of secant. It's the reciprocal of cosine. We're going to use the, the quotient rule. The derivative of the top is 0, and you multiply it by the denominator. You then subtract off, leave the numerator alone, and multiply by the derivative of the denominator, which is negative sine. This is all divided by the denominator, cosine of x, squared. What does this simplify to? Well, this is 0. I'm not going to write it. -1 times this negative becomes a positive, and I'm left with just sine. And I'll write my denominator as cosine squared of x. All right, for some reason, this is also the same thing as secant times tangent. And why might that be? Well, we can actually write the denominator as cosine x times cosine x. And the numerator, you can write it as 1 times sine of x. 1 over cosine is the definition of secant, and sine over cosine is the definition of tangent. So that is 1 over cosine of x becomes secant, and sine of x over cosine of x becomes tangent. And this proves our formula. All right, let's prove this formula. The way it's done is by rewriting cosecant as 1 over sine of x. Then we can now use the quotient rule to take the derivative. The derivative of the top is 0, times the bottom is just sine of x. Then minus, Okay, leave the top alone and multiply by the derivative of the bottom, and the derivative of sine is cosine. This is all divided by the denominator, sine, squared. Okay, how does this simplify? Well, 0 times sine is just 0. I'm not going to write it. -1 times cosine, I'll just put that as negative cosine. And my denominator is, well, that's sine squared of x. Why does this equal negative cosecant x times cotangent? Well, let's see, in the top, I can actually just remove the negative from the whole fraction. So it's negative whatever my fraction's equal to. The denominator is sine of x times sine of x, and the numerator is 1 times cosine of x. 1 over sine is cosecant. Cosine over sine is cotangent. So that is, we have negative 1 over sine of x times cosine of x over sine of x. These are the definitions of cosecant and cotangent. That proves our identity. Oh boy, one more. Okay, here we go. The derivative of cotangent of x apparently is negative cosecant squared of x. I think I know the strategy here. We're going to take the derivative of, well, the definition of cotangent is the reciprocal of tangent, which is cosine of x over sine of x. By the quotient rule, we'll take the derivative of the top. The derivative of cosine is negative sine of x. Then we will multiply by the denominator, which is also just sine of x. Then we're going to subtract off, okay, leave the numerator alone, that's cosine of x, and multiply by the derivative of the denominator, which is also cosine of x. And this is all divided by the denominator, which is sine of x squared. So what is this? Well, negative sine times sine, I'll just put that as negative sine squared of x. Okay, oh, this is negative cosine times cosine is negative cosine squared, so minus cosine squared of x. And this is all over, and I'll put sine squared x, like that. This numerator, I'm seeing I can factor a negative out from both terms, so I think I'm going to do that. I'm going to write this as negative. I'm seeing this negative here, so maybe I'll just leave that by itself. This is negative sine squared of x plus cosine squared of x all over sine squared of x. And just as a reminder, we have this identity that says sine squared plus cosine squared for the same angle x is equal to 1. Therefore, this is really negative 1 over sine squared of x because this numerator is really just 1. The definition of cosecant is 1 over sine, so this is negative cosecant squared of x. All right, if I want to graph the derivative of this function, I first want to know, where does this thing equal to 0, if ever? And I see there's one spot. That's right here. Looks like it's at -5. So I can actually plot 0. Where is the derivative negative? And where is the derivative positive? Wherever your function is decreasing, the derivative is negative. So that's going to be on the interval from -infinity to -5. And then it's increasing from 5 to infinity. So it's positive on 5 to infinity. So just kind of like as a reminder, down here the derivative is 0. To the left, it's negative. To the right, it's positive. I don't know the exact function, but my derivative will look something like this. A basic sketch, probably not perfect, but it gets these ideas across of where's it 0, where's it negative, and where's it positive. All right, so I want to sketch the derivative of this function. Where is it first equal to 0? Where does that happen? And then we'll figure out wherever it is negative, and then positive. I see there's one spot where it's 0, and it looks like it's right here. That looks like x is equal to 4. So I'll actually plot 0 right there. Wherever your function is decreasing, your derivative is negative. So that's going to be this part of the graph, which is from 4 to infinity. So we'll say that happens on 4 to infinity. Now your derivative is positive if your function is increasing, and that appears to be from negative infinity up to 4. So this is where the derivative is 0. Over here, it's positive, and over here, it is negative. So if I try to sketch this in, I don't know, maybe it looks something like this. Not perfect, but I think that's a general sketch of the derivative. If we want to sketch the derivative of this function by taking our same approach of, where is it 0? Where is it positive? And where is it negative? In this first part, we run into a problem. This function is always decreasing. It's never horizontal. This tells us that the derivative is never equal to 0. That never happens. Likewise, this thing is never positive. It's never increasing. It's only ever decreasing. Since this is linear, I know that the derivative has to be a constant number, and it must be equal to the slope of this line. So what is the slope of this line? What is that equal to? Okay, let's see. Slope is rise over run, so maybe I could use these 2 points to figure out the slope. This thing goes down 2 and over 4, and that means the slope is equal to negative 2 over 4, or negative 1/2. That's actually the value of the derivative. It's always that number. Let's see, if I try to sketch that in here, it's this horizontal line at negative 1/2. It's constant. It's never changing because the slope of this line never changes. All right, same idea for this one. Where is the derivative 0? Where is it negative? And where is it positive? The places where it's 0 is pretty easy to find. I don't know what they are exactly. There's a spot here, and there's a spot here. Looks to be close to maybe negative 3 and positive 3. Those aren't exact, but I'm just going to use those. I think it'll be close enough. Negative 3 and positive 3. Great. Everywhere else, it's either positive or negative. So since my function is increasing here and here, it must be that's where the derivative is positive. Here my function is decreasing, so my derivative is negative. So where is it negative? It's between the two values where it's 0. Where is it positive? On the outsides of these two values. Again, probably not exact, but it's good enough with the picture that we have. So my notes to myself are, okay, it's 0 here and here. Over here, the derivative is positive, then it's negative, and then it's positive again. Now, it's becoming more and more positive as I'm going in this direction, so it should be dropping down and becoming closer to 0. So I know it goes through this point and this point. The derivative decreases until it gets to 0. That means it's always positive. Between here and here, it becomes negative. It becomes more and more negative, but it has to go back to 0, so I get something that looks like this. And then over here, it has to be positive again. And in fact, it becomes more and more positive because this graph is becoming steeper, steeper, and steeper. And so I get this. This is a somewhat decent sketch of the derivative. All right, where's my derivative 0? Looks like this spot, and this spot. So answers may vary here, but it looks like maybe negative 4.5. I don't know, maybe something close to 1, and then maybe 3.5. Those are my guesses. It'll be good enough. So I know here, here, and here, the derivative is 0. All right, so where is it negative? That's wherever your graph is decreasing. That's going to be here and here. So in terms of intervals, that is from negative infinity up to, but not including, negative 4.5, but also everything from 1 to 3.5. All right, where's it positive? That's where your function is increasing. So this part and this part. So that's going to be from negative 4.5 to 1, and then from 3.5 to infinity. So my notes to myself are, it's 0 here, here, and here approximately. It is negative, then positive, then negative, then positive. So let's sketch this. Let's see what we get. Okay, it's a negative number, so it's not up here. So it's like a really negative number, but it's becoming closer and closer to 0. Okay, now it's going to be positive. It eventually has to come back down to 0. Okay, now it's negative, becoming more and more negative, but then less and less negative. And then it becomes more and more positive, like this. So here is a sketch of the derivative. All right, where is the derivative 0? Where is it negative? Where is it positive? All right, the places where it's 0 appears to be right about there, here, roughly there, and here. So it looks like 1, 2, 3, 4 places. Answers may vary. I'm going to say negative 4.8, maybe negative 1.4, maybe 0.8 and 4. Close enough. I think that's where it's 0. So I'm going to mark this spot, here, and here. Those are the places where the derivative is 0. That's 4 places. So that's 1, 2, 3, and 4. Around these values, it's either positive or negative. So where's it negative? That's any place where the function is decreasing. So that's here and here. 2 places. All right, so that's from, let's see, negative 4.8 up to negative 1.4, but also from 0.8 up to 4. Where's it positive? Everywhere else, where the function is increasing. So here, here, and here. Okay, so that's from negative infinity to negative 4.8, as well as from negative 1.4 up to 0.8, and from 4 to infinity. All right, let's draw this thing in. So it's positive, negative, positive, negative, and positive. All right, so let me see. It's going to drop down like this, come back up like this, go down like that, and then go up like this. I really don't know how high or low it's going in relation to what appears from my original function, but It's just a general sketch of what this thing looks like. Okay, here we're going to sketch the derivative of this function, which, well, this is the absolute value function. A big thing to point out for this problem is anything that is linear, the derivative is going to be the slope of that line. So what is the slope of this line here? It's going down 1 and over 1. So the slope here is -1. That means your derivative is constant. It's always -1. What is the slope of this line over here? It's +1. You go over 1 and up 1. Therefore, the derivative is constant. It's always +1. But what is the derivative at 0? F prime of 0 is, well, it does not exist. We defined a derivative at a point to be the limit from both sides, which on the left it's -1, on the right is +1, so you can't actually define it to be anything at 0. And I'll indicate this by putting an open circle here and here. So at this corner, the derivative does not exist, but everywhere else, it's either 1 or -1. All right, let's graph the derivative of this function. Well, anything that is linear, the derivative is going to be the slope of that line. So what's the slope of this line? Looks like it's going down 1, 2, 3, 4, and over 2. So the slope of this thing is -2. So I'm going to indicate that by drawing a horizontal line at -2. All right, what about this piece? What's the slope of this line? It's going over 1 and up 1. So the slope of this thing is always 1. Therefore, the derivative is constant, like this. What's the slope of this line? The slope of this line is 0. Therefore, the derivative of this part is 0. Kind of hard to see that, but I'm tracing along the x-axis. But what about the derivative at the individual points -3? What about the derivative at 2? These both do not exist. The reason is we get different derivatives on the left and the right. Therefore, we can't define it at either of those places. I'll indicate that with an open circle here and here, as well as here and here. So this is my derivative. Okay, what about this one? Oh my goodness. The derivative of this thing. Well, as I stated before, anything that is a line, the derivative is the slope of that line. And, well, this line has slope 1. You go over 1 and up 1. So for this part of the graph, the derivative is the horizontal line, 1. I already know the derivative is not going to exist at 2. So I'm going to say f prime of 2, it does not exist. That's because I know the slope from the right and the left is going to be different. So I'm going to indicate that with this open circle. So we have a couple open circle here's at once, just saying this spot doesn't exist on either the blue or the red graph. All right, well, what about the derivative of this piece over here? Well, we can analyze this by asking, is the derivative ever equal to 0? Is the derivative ever negative? Is it ever positive? And the answer this time is, well, yeah. At x equals 0, the derivative is 0 because we get a horizontal tangent there. So I can actually plot the point 0. The derivative is negative where the graph is decreasing. So that's from here to here, from 1 to 2, or sorry, from 0 to 2. And the derivative is positive here, from 0 to -infinity. What does this make your graph look like? Okay, well, it's positive and becoming more and more positive as we go in this direction. And then it's decreasing until you get to here. And I'll put an open circle at this one spot just to indicate that, well, it still does not exist at this point. And that's it. This would be the derivative. Yeah, these really just don't end. Okay, here we go. What is the derivative of this function? All right, this one actually is just 3 linear pieces, which means the derivative is going to be whatever the slope of these lines are equal to. So starting here, the slope of this line is 0, so I know the derivative is going to be 0. Here, the slope of this line is 1 over 1 up 1, so it's going to be 1. And then here, this line is decreasing with slope -1, so that's the derivative. It's -1. It's a pretty decent sketch of the derivative, but it's worth pointing out that, well, hey, what's the derivative at -1? It does not exist. We get 2 different numbers on the left and the right side, so we can't define it as one value at -1. And the same thing holds true for the derivative at 5. It also does not exist. So I'll put an open circle here, an open circle there, as well as one here and here. And this is the derivative.